In this video, we're going to be going over an example related to design concepts. I'll let you pause the video so you can read over the question and attempt the question on your own if you want. Okay, so in the question, we're told to select the lightest weight steel wide flange beam from the appendix that can support this load. We're given the allowable bending stress and the allowable shear stress. Since we're also given the live load deflection equation, we can assume this load here is a live load. Let's start with the first step, which is performing an analysis for the given loading conditions. First, we need to find the support reactions. We'll call this point A. Since point A is a fixed support, we'll have these forces acting on the support. Since AX is the only horizontal force, it will be 0, so we can ignore it. We'll take the summation of forces in the y direction and assume upwards to be positive, and we'll end up with this. Remember to convert the distributed load into a point load, which in this case would be the area of the triangle load. And we'll end up with AY equals to 24 kip, which is also 1,000 pounds force. To find AM, we take moment about point A and assume counterclockwise to be positive, and we get this equation. This is simply the point load of the triangular load, which is located here, and the distance to point A is simply the length of the beam divided by 3. Simplifying, we get AM equals to 48 kip feet. Then we can draw our shear force diagram and bending moment diagram. Now we can locate the maximum shear force and maximum bending moment from the diagrams. And we get the maximum shear force to be equal to 24 kip at point A. And for maximum bending moment, we get 48 kip feet, also at point A. Now, onto step 2, where we design for bending. Since the bending stress we're given is in inches, we'll convert the maximum bending moment to inches as well. Then we can plug the maximum moment into the required section modulus equation, and we'll get that the required section modulus is 24 inches cubed. Now that we have our required section modulus, we can select our steel shape from Appendix C and choose the lightest shape possible. From the table, we can see that from all the different designs, the lightest shape is W12 by 22, because it has a section modulus of 25.4 inches cubed. Now we want to add the self-weight to the beam and check if it's adequate. The free body diagram will look like this. And then we can find the reaction forces at the fixed support, which will be this. Then we can draw our shear force diagram and bending moment diagram. And with these, we can locate the maximum shear force and bending moment. With the maximum bending moment from just the weight of the beam we selected, we can check if our design meets the bending stress requirements. In order for us to continue with the selected design, the maximum bending stress that we calculate must be less than or equal to the allowable bending stress. We have to use the total maximum shear force and total maximum bending moment values when we calculate for the maximum bending stress and shear to account for the given loading and the weight of the beam. So we'll add together the maximum shear force of the given loading plus the self-weight of the beam. We'll do the same for the total maximum moment as well. As you can see, we converted the total maximum moment to inches because the section modulus is in inches. We can plug our values in and we get a maximum bending stress of 22.86 KSI, which is less than the allowable bending stress. So our selected design meets the bending requirements and is okay to use. Now we want to verify our selected design to see if it meets the shear requirements. What we have is a wide flange beam, so we'll use this equation. Tau max equals to Vmax over A web. Vmax is simply the total maximum shear force from the live load in the question, in addition to the weight of the beam. So we'll have 24.13 kip. The area of the web is simply a web equals to the depth multiplied by the web thickness, TW. From Appendix C, the depth for a W12 by 22 beam is 12.31 inches, and the web thickness is 0.260 inches. So multiplied together, the area of the web is 3.2 inches squared. Now we can plug everything into the maximum shear stress equation, and we'll end up with 7.54 KSI. 7.54 KSI is less than 14 KSI, which is the allowable shear stress we're given. So then our selected section is okay for shear. Therefore, we would use a W12 by 22 beam. Since there are no fasteners, we can move ahead to the next step, which is to check the deflection. Note that the deflection limits usually only apply to live loads and not the self-weight of the beam. So we'll only calculate the deflection due to the triangular load. If we take a look at the beam tables and find the one with a triangular load similar to the one in our question, we can see that the maximum deflection equation will be this. From Appendix C, we can find the moment of inertia. And for E, the modulus of elasticity for all steel structures is 29,000 KSI. Now we have all the values to calculate for the maximum deflection, and we can plug it into the equation and solve. And we'll get 0.132 inches. Next, we can calculate the maximum allowable deflection using the live load deflection equation, which is allowable deflection equals to L over 360. We'll convert the length of the beam to inches first, and then plugging in the value, we get 0.200 inches. By comparing these two values, we can see that the maximum deflection is less than the maximum allowable deflection. So our selected design satisfies the deflection requirements. Therefore, in our final answer, we should use a W12 by 22 beam because it satisfies the bending, shear, and deflection requirements and is also the lightest shape. In conclusion, we were able to apply the general design process of beams into this example, where we were able to choose a beam that is able to support the given loading. That concludes this video, and that also concludes the course content.